Momentum is a concept that has to do with both the mass and velocity of an object. One way of thinking about it is that the more momentum an object has, the less you would want to get hit by it. Because if something's bigger, it's going to hurt more. If something's moving faster, it's going to hurt more. So that's one way of thinking about it. The term that I like is oomph, how much oomph an object has. But anyway, the a more technical way of stating it is, you could say that the momentum an object has is a measure of how much you would need to put into it to stop it. It's along the similar lines to kinetic energy, but it's not quite the same. So let's take a look at where this is derived from. We know that our net force is equal to mass times acceleration. That's Newton's second law. From our kinematics, we know that acceleration is defined as the change in velocity over time. So just making a simple substitution here gives us that F net equals m delta v over t, and this gives us that F times t equals m delta v. This side of the equation, this is an equation that we will use very frequently. This side of the equation here is momentum. mv is momentum. And for whatever reason, momentum is lowercase p. I have no idea why it's p. I mean, I guess m was already taken for mass, but p just seems random. Anyway, so this is a change in momentum over here. Ft is called impulse. And again, for whatever reason, that gets a J. Okay, so this equation is known as the impulse momentum theorem. Very creative name, I know. So you could also write this J equals delta P, but this is probably more useful most of the time. This is a force times a time, so our units for impulse are Newton seconds. Mass times velocity is kilogram meter per second, and these in fact are equivalent because a Newton is a kilogram meter per second squared. So multiplying by seconds cancels out one of the seconds, and that leaves you with kilogram meter per second. Now, for whatever reason, again, impulse is usually given in Newton seconds, and the unit is usually given as Newton seconds, and momentum is usually given as kilogram meters per second. So that is, even though they're equivalent, that's what is conventional. Yeah. Now this equation tells us, well, first off, these are both vectors. Both impulse and momentum are vectors. And this equation, there's some conceptual stuff embedded in this equation, in that the longer a force, the more time a force is applied for, the more the momentum of an object changes. Also, this tells us if momentum is changed in a very short amount of time, then the force is large. And this is the case, the most common case of this is when you drop something and it hits the floor, it comes to a stop over a very short amount of time, so there's actually a pretty large force involved in that. Here's another case where there's going to be a large force because the time is small. Say a baseball with mass 0.14 kilograms has a speed of 38 meters per second as it approaches the bat. The ball is hit, leaving the bat with a speed of 58 meters per second. We're going to assume the initial final velocities are in opposite directions so we don't have to worry about any vector stuff. So the first part of the question is to determine the impulse applied by the bat. Impulse, remember, is this whole left side of the equation, this force times time. And so our impulse is just equal to our change in momentum, m delta v. Our mass is 0.14. I didn't give you which direction is positive, so the sign of this is going to be arbitrary. But it leaves the bat with speed 58. It came toward the bat with speed 38. Key thing to remember is that these are in opposite directions. So if I say that 58 is positive, then the 38 has to be negative. And we can punch that into the calculator. 0.14 times 58 plus 38, and get that our impulse applied is 13.44 Newton seconds. Now, if the ball and the bat are in contact for 1.6 times 10 to the minus third seconds, well, we know impulse is equal to force times time, so that 13.44 is equal to force times 0.0016. And so we get the force in question is 8,400 newtons, which is really big, but actually not particularly unrealistic for that kind of collision. Now, impulse momentum theorem is also a way that we can go about problems that we could have solved using a combination of force and kinematics. Let's say you have a car with mass 2,300 kilograms. It has a net force of 7,800 newtons acting on it for 3.2 seconds. By how much does its momentum change? Well, we know our impulse is equal to change in momentum. So our change in momentum is just equal to force times time, which is 7,800 times 3.2. 7,800 times 3.2. Punch that in, whoops, and you get that we have 24,960 kilogram meters per second. Take note that the mass hasn't come into play yet. Oops, the mass is up here. The mass hasn't come into play yet. So how much the momentum of an object changes is independent of the mass. How much its velocity changes will depend on the mass. But if you exert a force on two objects, it doesn't matter which one has more mass. The momentum change is going to be the same if you exert the same force for the same amount of time. But the velocities will be different. And by how much does its velocity change? Well, change in momentum is just mass times change in velocity. And so we have 24,960 is equal to 2,300 delta V. And so we can punch that in, divide that by 2,300, and find that our delta V is about 10.85 meters per second.